considering an undamped SDOF system subjected to free vibration. For this scenario, the equilibrium equation is simplified, where both external force and damping force terms are taken as zero. What we have now is a homogeneous equation. Since the term acceleration, which is also the second-order derivative of displacement x, is included in this equation, it is also known as second-order differential equation. The solution of x may appear in the following form. To apply this, we first make sure the dynamic responses are expressed in the form of partial derivatives with respect to time. Then, we obtain the solution for acceleration in exponential form by determining the second-order derivative on the solution for displacement. After that, we substitute the trial solution into the equilibrium equation, and from here, we may simplify the equation again. The equation is now in the form of a b equal to 0. In this form, either a or b should be 0 to make this equation valid. Knowing the exponential terms is always positive, we can deduce that the product of m lambda squared plus k is 0. Focusing on this part and let's express lambda in terms of m and k. To ease our further operation, we introduce a new term that represents the surd of k over m. There are now two possible answers for lambda, and when we include both in our trial solution of x, we change its form. From here, based on Euler's formula, the solution is shifting its form again, where trigonometric functions are now introduced. By rearranging and simplifying the equation, we are now establishing two constants. By applying the initial conditions, we know the first constant C1 equals to the initial displacement. Next, we define the partial derivative of the solution for x that consists of C1 and C2. Again, by applying initial condition, we solve for C2 as well. Thus, we have now obtained another form of solution for x, and that for acceleration from second-order differentiation. By substituting the sinusoidal form solutions into the equilibrium equation, we eventually express it in the simplest way. The angular frequency of the undamped system equals to the square root of k over m. It is also known as natural frequency of the system, which is the frequency at which the system tends to oscillate without damping. The period can be calculated by dividing 2 pi with that frequency. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.